In this lecture, we will talk about the criteria of a good estimator. We have to understand what do we mean by good. In the previous lecture, we talked about the problem of statistical inference. We spoke that there are basically two types of statistical inference. One is estimation and the other is testing of hypothesis. Estimation, we said, it is of two types, point estimation and interval estimation. In this lecture, we will concentrate on point estimation. In point estimation, we spoke about two things, an estimator and an estimate. What is the difference? Let me just recollect the thing. The statistic which is used to estimate an unknown parameter is called an estimator, and its value for a given set of sample observations is called an estimate. So here, in this lecture, we will talk about how to decide on which estimator we should use to make inference about an unknown parameter. So the problem is that in a given statistical inference problem, that means when we estimate an unknown parameter, we may have several estimators. Like, suppose we want to estimate the population mean. We can either use sample mean or one can use sample median. The problem is to decide which estimator we will use, or in other words, which estimator will be eligible to estimate this unknown parameter. In other words, we have to think of the eligibility of a good estimator. There are basically two criteria through which we will decide whether a given estimator is good or not. The first criteria is unbiasedness. A statistic T is said to be an unbiased estimator of a parameter theta if expectation of T is equal to theta, whatever be the true value of theta. Now, whatever be the true value of theta has got some special meaning. Expectation of T is equal to theta. That we can understand. We know what is expectation. But this will not depend on the value of theta. That means we won't say that for these values of theta, T will be an unbiased estimator of theta or expectation of T will be equal to theta, and for these values of theta, expectation of T will not be equal to theta. It will not be something like this. If expectation of T is equal to theta, whatever be the value of theta, then we will say that T is an unbiased estimator of theta. Why this is a criteria of a good estimator? Because we know expectation is nothing but an arithmetic mean in the probability setup. What is arithmetic mean? Arithmetic mean is that value around which other values are clustered. We spoke about sampling distribution earlier. That means the value of T may vary from one sample to another. If I take a sample of 100 individuals, I'll get one value of T. If I take another sample of 100 individuals, we may get another value of T. So in a given situation, we will observe only one sample. So I'm not sure whether that value of T will be close to theta. But if we have this result in my hand, that is if expectation of T is equal to theta, then we can say that the values of T will get clustered around theta. So whatever sample I observe, I will calculate the value of T out of that sample. This result will guarantee that that value of T will be close to theta. That means our guess will not be too bad. That is why expectation is unbiasedness is a desirable criteria. We take an example. Suppose P is the probability of getting head in a single toss of a coin, and we want to estimate P. Not all coins are unbiased, so blindly we cannot say that P will be equal to half. I don't know which coin I am given, so we have to estimate P. Now we have to generate sample. How can we generate sample? Suppose for this purpose we toss the coin n number of times, and let x be the number of heads obtained in these n tosses. Clearly x will follow a binomial distribution with parameters n and p. So we'll have expectation of x is equal to np. So if I take n to the left hand side, then expectation of x by n will be equal to p. Observe that here we are not talking about any particular value of p. This is a general result that expectation of x by n will be equal to p. So that means x by n will be an unbiased estimator of p according to the definition of unbiasedness. What is x by n? N number of tosses, x is the number of heads. So x by n is nothing but the sample proportion of getting heads. And what is p? The probability of getting head. So p is nothing but the population proportion of heads. So we can see that x by n, the sample proportion of getting heads, is an unbiased estimator of p. We now go to a second example. Suppose we have a random sample x1, x2, xn drawn from a population with mean mu and variance sigma square. Since x1, x2, xn is a random sample, we'll have expectation of x1 is equal to mu, expectation of x2 is equal to mu, expectation of x3 is equal to mu, and so on. So in general, we can write expectation of xi is equal to mu for all I running from 1 to n. Further, we consider the expectation of x bar the sample mean. So expectation of x bar, you can see the mathematics on your slide. It is expectation of 1 by n summation xi. Now we take expectation inside. So we'll get 1 by n summation expectation of xi. So we have got 1 by n summation mu, because expectation of xi is mu. So that means summation mu will be n mu. Mu is being added up n times. So n mu divided by n. So it will be mu. So you see, expectation of xi is equal to mu for all I running from 1 to n. So how many unbiased estimators of mu we have got? N. x1 is an unbiased estimator, x2 is an unbiased estimator, xn is an unbiased estimator. So n. Further, we have seen that expectation of x bar is also equal to mu. That means x bar is also an unbiased estimator of mu. So how many unbiased estimators of mu we have got? N plus 1. So the problem is to choose the best among these n plus 1 unbiased estimators of mu. I hope you have understood the problem. Our problem is to estimate the population mean mu. But we have got n plus 1 unbiased estimators of mu. That means x1, x2, xn and x bar are equally good for estimating mu as far as unbiasedness is concerned. But intuitively, which one would you choose? Say, let me lead you to this question. We want to estimate the population mean, say population mean income. x1, x2, xn are the incomes of first person, second person, nth person. And x bar is the average income of these n persons. Now, as far as unbiasedness is concerned, income of the first person is an unbiased estimator of mu. Income of the second person is an unbiased estimator of mu. Also, in this way, income of the nth person is unbiased estimator of mu. Also, the average income of these n persons is unbiased estimator of mu. Now, do you think all these estimators are equally good, or we have to search for some other criteria? So it is very evident that all these estimators cannot be equally good. So that means only with unbiasedness we cannot decide whether an estimator is good or not. So we thus need a second criteria. The second criteria is called minimum variance. A statistic T is said to be a minimum variance unbiased estimator. We abbreviate this as MVUE of a parameter theta if. Let us see the criteria minimum variance unbiased. What is the last criteria? Unbiased. So that means the statistic has to be unbiased. So we have the first condition, expectation of t is equal to theta, whatever be the true value of theta. Next we talk of minimum variance. That means variance of t will be less than or equal to variance of t dash, where t dash is any other unbiased estimator of theta. That means you think of all possible unbiased estimators of theta, we'll choose that estimator which has got the minimum variance among these unbiased estimators. So that is why we say variance of t is less than or equal to variance of t dash, where t dash is any other unbiased estimator of theta. So in general, what do we mean by an MVUE or a minimum variance unbiased estimator? It is such an estimator which has to be unbiased firstly, and which must have the minimum variance among all possible unbiased estimators of theta. In this sense, this estimator will be called a minimum variance unbiased estimator. We go to the second example once again. In the present case, we have, since x1, x2, xn is a random sample drawn from a population with mean mu and variance sigma square, So we must have variance of xi is equal to sigma square for all I. We now compute variance of x bar. Variance of x bar will be variance of 1 by n summation xi. 1 by n, if it comes out of the variance, then it will be 1 by n square. So 1 by n square variance of summation xi. Xi's are independent, as we have said, random sample. So variance of x1 plus x2 plus xn will be variance of x1 plus variance of x2 plus variance of xn. So notationally we can write 1 by n square summation variance of xi. So again 1 by n square summation sigma square, because variance of xi is sigma square for all I. So n sigma square by n square, so it will come out as sigma square by n. Now see, what was variance of x1? Sigma square. Variance of x2? Sigma square. Variance of xn? Sigma square. So those n unbiased estimators, x1, x2, xn, each has got the variance sigma square. What is the variance of x bar? We have just worked out sigma square by n. So among these n plus 1 unbiased estimators of mu, which has got the minimum variance? Minimum variance is attained by x bar. So here x bar is the best among these n plus 1 unbiased estimators of mu. Just hold on the idea of minimum variance unbiased estimator. We'll come back to this a bit later. Now see, can we say x bar is the minimum variance unbiased estimator? See, we have not compared the variance of x bar with the variances of all possible unbiased estimators of mu. We have compared variance of x bar only with the variances of the n other estimators, x1, x2, xn. If I say x1 plus 2x2 plus x3, first of all, will this be an unbiased estimator of mu? Definitely. You take the expectation, it will be expectation of x1 plus 2 into expectation of x2 by 3. So expectation of x1 is mu, expectation of x2 is also mu. So it will be mu plus 2 mu by 3. So it will be mu. So that means x1 plus 2x2 plus 3 is also an unbiased estimator of mu. Did we compare variance of x bar with the variance of this estimator? No. Take one more. x1 plus 5x2 plus 9x3 by 15. Is this an unbiased estimator of mu? See, its expectation will be expectation of x1 plus 5 into expectation of x2 plus 9 into expectation of x3 by 15. So mu plus 5 mu plus 9 mu, that is 15 mu by 15 mu. So the second one, x1 plus 5x2 plus 9x3 by 15, is also an unbiased estimator of mu. Did we compare variance of x bar with the variance of this estimator? No. That means we can find out at least two estimators which are unbiased for mu, but we have not considered these two estimators. So that means what I want to say is this: we did not compare variance of x bar with the variances of all possible unbiased estimators of mu. That is why we cannot say that x bar is the minimum variance unbiased estimator. We can only say that x bar is the best among the n plus 1 unbiased estimators that we have considered. Let me tell you, in our course of study, we will never go for finding out the minimum variance unbiased estimator, because the theory of finding out minimum variance unbiased estimator is altogether different, which is out of the scope of this course of study. Simply because there is another approach which is called Cramer-Rao lower bound. It can be shown that any minimum variance unbiased estimators, the variance of any minimum variance unbiased estimator attains that lower bound. We are not going into that approach. What we will do, please try to understand this very carefully. What we will try to do in our course of study is this: given a number of unbiased estimators, we will simply try to find out the best among these unbiased estimators. A minimum variance unbiased estimator is unique in the sense that for a given parameter, we'll have only one minimum variance unbiased estimator. Suppose x1, x2, xn is a random sample drawn from a population with mean mu and variance sigma square. It can be shown that the sample mean x bar, 1 by n summation xi, is the minimum variance unbiased estimator of mu. So x bar has got nice properties that you must appreciate. So that is why we always talk about mean, then median, mode, etc. Let us take a problem to understand more about how to find out the best estimator in a given situation. Suppose we have T1, T2 and T3, T independent unbiased estimators of a parameter theta, each having the variance k. We have to find the best among the following estimators of theta, which are given t1 plus 2t2 plus t3 by 4. This is the first one. t1 plus t2 plus 3t3 by 6, the second one. And t1 plus t2 plus t3 by 3, the third one. So we have to find the best among these unbiased estimators for estimating theta. So what should be the steps that we'll follow? What do you think? So to choose the best among these unbiased estimators of mu, we have two criteria in our hand. One is unbiasedness and the other is minimum variance. First, we'll check which of these estimators are unbiased for mu. Let us see the solution. We are given that T1, T2 and T3 are all unbiased estimators of theta. That means expectation of T1 will be equal to theta, expectation of T2 will be equal to theta, expectation of T3 will also be equal to theta. And we are given that the variances are all equal to k. So variance of T1 will be equal to variance of T2 will be equal to variance of T3, and that will also be k. We are also given an important condition that T1, T2 and T3 are independent. So as I mentioned, we will first find out among the three given estimators which are unbiased for theta. We first compute the expectation of the first estimator, that is T1 plus 2T2 plus T3 by 4. So 1 by 4 will come out. It will be expectation of T1 plus 2 into expectation of T2 plus expectation of T3. So it will be 1 by 4 theta plus 2 theta plus theta. That comes out to be theta. That means the first estimator T1 plus 2T2 plus T3 by 4, this will be an unbiased estimator of theta. Next we compute the second expectation of the second estimator. Expectation of T1 plus T2 plus 3T3 by 6. So 1 by 6 will come out. It will be expectation of T1 plus expectation of T2 plus 3 into expectation of T3. So that will be equal to 1 by 6 theta plus 3 theta. That means 5 theta by 6. Is this equal to theta? No. So that means expectation of the second estimator, that is T1 plus T2 plus 3T3 by 6, is not equal to theta. That means the second estimator is not an unbiased estimator of theta. Let us go to the third one, then we'll come back. Expectation of T1 plus T2 plus T3 by 3. So that is 1 by 3 ET1 plus ET2 plus ET3. So that is 1 by 3 theta plus theta plus theta. So 3 theta by 3 theta. So that means the third one is an unbiased estimator of theta. So that this brings us to the fact that among the three given estimators of theta, 2 are unbiased for theta. That means 1 and 3 are unbiased for theta. Now we have to choose the best among these 1 and 3. That means we have to go to the second criteria, the criteria of minimum variance. So we'll consider that unbiased estimator to be the best, which is the minimum variance among these two unbiased estimators of theta. So we have to compute the variances of these two unbiased estimators. Variance of T1 plus 2T2 plus T3 by 4. 1 by 4 will come out as 1 by 16. So variance of T1 plus variance of 2T2 will mean 2 will come out, 2 square, 4 variance of T2 plus variance of T3. T1, T2 and T3 are independent, so there will be no covariance term. Variance of T1, variance of T2, variance of T3 are all equal to k. So it will be, in the bracket, it will be k plus 4k plus k, so 6k by 16. So that is 3 by 8 in k. So this is the variance of the first unbiased estimator. The variance of the second unbiased estimator, that is variance of T1 plus T2 plus T3 by 3. 1 by 3 will come out as 1 by 3 square, that is 1 by 9. So inside the bracket, we'll have Vt1 plus Vt2 plus Vt3. So 3k by 9. So that is 1 by 3k. Now, if we compare the two variances, 3 by 8k and 1 by 3k, definitely 1 by 3k is less than 3 by 8k. So that means T1 plus T2 plus T3 by 3 has got the minimum variance among the two unbiased estimators of theta. So T1 plus T2 plus T3 by 3 is the best among the three given estimators of theta. Among the three given estimators of theta, we were given 3 estimators. From the first criteria, we filtered out 2 estimators, the first and the third one, by the criteria of minimum variance. And by the second criteria, we decided upon which is the best among these two unbiased estimators. Now, sometimes we commit a mistake. What is that mistake? We compute the expectation of the three estimators. We find that the first and the third estimators are unbiased for theta, while the second is not. Then we compute the variance of all the three estimators. Suppose I find that the variance of the second estimator is minimum, which is not unbiased. Now, shall I say that the second estimator is best among the three estimators? No. A big emphatic no. Because the second estimator fails to satisfy the first condition, fails to satisfy the first criteria. So the second estimator cannot be best. Firstly, all the estimators are to be unbiased, and from the unbiased estimators only, we'll choose the best one, which has got the minimum variance. Now we come to another important definition, which is called best linear unbiased estimator. Like minimum variance unbiased estimator, we define best linear unbiased estimator. Here we have three criteria: best, linear, unbiased. We start from the end, unbiased. That means the statistic or the estimator has to be unbiased. Expectation of t has to be equal to theta, whatever be the true value of theta. Linear. Linear in the sense that t has to be a linear function of the sample observations. That means t will be some sort of summation a1 ai xi, that is a1 x1 plus a2 x2 plus a3 x3 plus dot 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 plus an xn, a linear function of sample observations. Now the third criteria is best. Best in the sense of minimum variance. That means variance of t has to be less than or equal to variance of t dash, where t dash is any other linear unbiased estimator of theta. So that means minimum variance unbiased estimator means what? Minimum variance among all possible unbiased estimators. But here we are adding one more criteria, that is that estimator has to be linear as well. Now we talk about a result. Again we will praise x bar, the arithmetic mean. x1, x2, xn is a random sample from a population with mean mu and variance sigma square. It can be shown that x bar is the best linear unbiased estimator. X bar is the minimum variance unbiased estimator. We know what is x bar. X bar is 1 by n summation xi. So that is basically 1 by n. Then within bracket we can write x1 plus x2 plus dot 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 plus xn. That means x bar is a linear function of sample observations. So that is why x bar is the best linear unbiased estimator. Another very, very important result. x1, x2, xn is a random sample from a population with mean mu and variance sigma square. Then s naught square, that is 1 by n summation xi minus x bar whole square, is not an unbiased estimator of sigma square. Earlier, you have learned the formula of variance as 1 by n summation xi minus x bar whole square. But this is not an unbiased estimator of sigma square. On the other hand, 1 by n minus 1 summation xi minus x bar whole square, which we may denote by s square, can be shown to be an unbiased estimator of sigma square. If you can recall, in the earlier lecture, we talked about a result when x1, x2, xn is a random sample from a normal population. We defined x bar as the sample mean and s square as 1 by n minus 1 summation xi minus x bar whole square, and we said that x bar follows a normal mu sigma square by n distribution. On the other hand, n minus 1 s square by sigma square follows a chi-square distribution with n minus 1 degrees of freedom. So at that time also I said that we will justify why we are taking 1 by n minus 1 instead of 1 by n. This is the justification, because 1 by n summation xi minus x bar whole square is not an unbiased estimator. On the other hand, 1 by n minus 1 summation xi minus x bar whole square is an unbiased estimator of the population variance sigma square. So from now on, whenever we say about sample variance, we will consider 1 by n minus 1 summation xi minus x bar whole square. There are some important definitions. First, we talk about bias. Suppose an estimator is not unbiased. That means what? It is biased. A statistic t is said to be a biased estimator of a parameter theta if expectation of t is not equal to theta. The bias of t is defined as expectation of t minus theta. T is said to overestimate or underestimate theta if bias of t is greater than theta or bias of t is less than theta, respectively. On the other hand, if bias of t is equal to 0, then we say that t is an unbiased estimator of theta. Now, can you tell me why do we say that t overestimates theta when bias is positive and T underestimates theta when bias is negative. Bias of T is positive means expectation of T is greater than theta. Bias of T is negative means expectation of T is less than theta. That is why we say overestimate or underestimate simply. Mean square error. This is another measure of error, that is expectation of T minus theta whole square. And mean absolute error, this is another definition which we seldom use, that is expectation of the absolute value of T minus theta. That means these are all measures of errors that we may commit in estimation. Now we will go to two other concepts of estimation which are called consistency and efficiency. These two basically deal with the large sample behavior of a statistic. If we consider any estimator T of theta, then from T we can have a sequence Tn just by varying the sample size n. If we increase the sample size, obviously the estimator will get changed, incorporating more and more sample observations. Obviously, when we go on increasing the number of sample observations, we will expect that the distribution of T will be more and more concentrated around the parameter theta. An estimator having this property is said to be consistent. That means with more and more sample observations, if the distribution of T becomes more and more concentrated around theta, that means if we can estimate theta more and more precisely with increase in the sample size, then that estimated T will be said to be consistent. Now, in any particular situation, there may be several consistent estimators. In fact, if we can find out one consistent estimator, we can show that from that consistent estimator, we can construct many other consistent estimators. So again, there is a problem of choice, like unbiased estimators. So we have a number of consistent estimators. So what we can do? We have to choose the best among these consistent estimators. But here we'll not go solely on the variance criteria. Let us see. So first, we have to consider that consistent estimator to be the best for which the asymptotic variance, that is the large sample variance, is minimum. Asymptotic variance means large sample variance. But not only this, we'll consider those consistent estimators whose asymptotic variance is normal. This consistent estimator is called an efficient estimator. So this is the idea of consistency and efficiency. These when we deal with large sample properties of statistics or estimators, then these two properties are used. But we have to remember one fact, that given a set of estimators, if you are to choose the best among these, first we shall go for unbiased test, and then among the unbiased estimators we'll choose that one which has got the minimum variance. Thank you.